So I am going to talk about energetic and nitrogen efficiency and try to integrate them, okay? One of the things that I want to recognize, and I'll get to a couple slides on this, cows are changing and we need to be conscious of this. Today's cow is not 20 years ago cow, right? Today's cow is very different, and the more we learn about these cows, the more I think we are, I'll say we're grossly underestimating their requirements. And I'll give you some examples of that, and I'll show you a couple herds, right? On an energy basis, the answer is no. On an amino acid and fatty acid basis, I say that answer is yes, and that's where I want to go with this. The other thing is that when I say protein synthesis, this always gets confused, and I think when I listen to a bunch of my colleagues who are going to speak today, and historically, when we talk about protein synthesis in the mammary gland, everybody kind of diverts to milk protein synthesis, and not just protein synthesis in general. Protein synthesis is important because it's not just milk protein that gets made with protein synthesis. Lactose and fat also get made with protein synthesis, right? It's all enzymes and things like that that are required. So I think we have to keep that in mind, and that it's not just a straight line into milk protein when you're talking about amino acids. And I think the other thing, and again, I'm going to go fast here, the concept of nitrogen efficiency is really energy dependent. And in a ruminant, I'm going to argue that it's a little bit energy dependent on the back end of the cow, but on the front end of the cow, we get confused with the type of nitrogen that will end up in the urine, more the RDP, if you want to use that term, than intake into milk, right? And I think we've got to start looking at this urinary end more closely, because I'm not sure we can always change overall nitrogen efficiency, but we can get rid of the stuff that she's going to pee away. Right, and anyhow, there's a lot of things related to protein efficiency that's tied, or nitrogen efficiency that's tied to energetic efficiency. And that's, this is a tough metrics because they require non-protein nitrogen for rumen function, right? And we just kind of want to pile it all together as in crude protein or nitrogen intake, and I think we have to start separating them out. And we've been working on the CNCPS in version 7, and I think if there's anything that we probably worked the hardest on is to separate ruminal requirements from post-ruminal amino acid requirements, to isolate that rumen to make sure that we can solve that problem and then move on to the rest of the cow. All right, because when you describe nitrogen efficiency for non-ruminants, they're really talking about amino acids. And if we look at most dairies, right, on-farm efficiencies, they range from 20 to about 32. They're a little bit higher than that now. We're doing much better at the high end. I'm going to come back to that. If we look at theoretical limits, it's somewhere between 40 and 45, and there's been lots of publications on that. I would argue that the practical level, somewhere between 38 and 40 in high groups. It can be useful, right? But we got to extend it to whole body nitrogen metabolism and not just milk. And I think that's where we also get confused. It's productive nitrogen and not just milk nitrogen. If I look at this group of cows here, again, I got to go fast. 120 days in milk, 60 pounds of intake, 15.8 on protein, average nitrogen efficiency, 38%. And this is productive end to intake end. We studied this group of cows for 4 months, modeled through it. What we realized is the cows at the high end of production, they were making about 168 pounds of milk at the time. This is 15-year-old data. Their nitrogen efficiency at the high end of production was about 41%, right? That was informative to us because that basically said they're right at the theoretical limits already in commercial herds. So it said that probably isn't, those limits that we have, or those higher levels are not probably all that correct. It's probably higher if we can figure this all out. And if we look around the world, the Netherlands has been a big part, in the Po Valley in Italy. We're getting to the same point. New York is starting to look at this. We got to reduce our protein feeding, right? There's too much ammonia out there. Well, recently there's been a lot of work. Kristen Reed looked at the effect of overfeeding nitrogen or nitrogen excretion in the urine on ME-allowable milk. And they realized that if we overfed nitrogen, it increased heat expenditure, which reduced energy for productive function. And there was more of an effect on RDP, or the rumen available nitrogen, than RUP, right? 1.1 versus 0.78 mcals per kilogram. So it basically says as we overfeed rumen available protein, we reduce the amount of energy available for milk and component synthesis. And it doesn't look like it's the urea cycle energy, right? We used to focus on the cost of synthesis of urea. That doesn't look like that's the sole energy expenditure on these cows. The work done at Nebraska, Morris demonstrated that increased urinary nitrogen excretion decreased ME content of the diet as calculated from DE, right? And they were able to calculate this urinary energy output anywhere from about 1,400 to 3,100 kcals, and urinary nitrogen ranged from 85 to 220 grams, or about 20 to 60% of nitrogen intake. And I think that's pretty telling, right? Anywhere from 20 to 60% of nitrogen intake. Well, if she's going to pee out 60% of her nitrogen intake, that's a big waste, right? Whether you change overall efficiency of intake nitrogen to milk is kind of irrelevant there, because she's just saying, hey, I don't need it, I'm going to pee it away. And they could calculate an equation to predict that. And it just says we need to account for urinary nitrogen when we're trying to accurately predict ME, but we're also going to make the cow more efficient if we reduce that, right? Cows are great recyclers, right? And you know, we can spend a lot of time here. In the interest of it, you know, ammonia is going to come out of the rumen, it's going to go to the liver, it's going to be converted to urea, it's going to move into the bloodstream. We're going to have a pool. It's going to be, you know, filtered by the kidney. If the kidney says, together with the brain and the liver says we don't need it, they're going to put it in the urine. If they do need it, they're going to put some back in here, and then it's going to recycle back to the gastrointestinal tract. Every time we can get it to come back here, we can increase efficiency, but that's dependent on reducing this nitrogen intake a little bit, because if we feed too much here, the probability that the recycled urea gets captured goes down. It really becomes a probability function in that rumen. All right. And that was really well demonstrated in this review by Chris Reynolds and Niels Christensen, where they showed this beautiful sigmoidal curve. And this is beef and dairy cows. This is the fraction of urea entry rate, so that's urea production in the liver, and this is dietary crude protein, right? And this is going back to the gastrointestinal tract. And you can see at the low crude protein levels, or the low nitrogen intake levels, there's nothing, you know, basically leaving the rumen. And then as we increase the crude protein, more and more of that, you know, does not get recycled back to the gastrointestinal tract, or doesn't get captured. Either way, we could do the couple different calculations here. And we tend to operate here, right? We tend to operate out here. So we're really not looking at a lot of that nitrogen going back into the gastrointestinal tract. Inversely, it goes out in the urine. So if we want to make the cow more efficient, independent of the amount of nitrogen going into the milk, we've got to work back down this line, basically reducing the amount of nitrogen we feed, but ensuring that this nitrogen that will recycle back to the gastrointestinal tract is going to be captured, right? So there's a balance there. We can do that by looking at urinary nitrogen and rumen N balances, and that is a way to solve this problem. So we put this in a paper in 2015. And what we did here is we held all these are all cows where they had done nitrogen recycling experiments. And if you look at this, this is where dietary energy is not first limiting, right? So you're looking at the effect of protein. So what you're saying here is that, you know, when there's equivalent energy across all these treatments, milk nitrogen, and this is crude protein converted to a nitrogen, or this is true protein converted to a nitrogen basis, there's no change, you know, from about 14 to 18, 19% crude protein, there's no change in milk nitrogen output. There's really no major change in fecal nitrogen, but there's a big change in urinary nitrogen, and most of our cows are operating here. And the first step would be to get us to at least a one-to-one relationship between milk N and urinary N, or productive N. I'll argue for productive N and urinary N. And then if we're really good, we can be down here at like 0.12 or 0.13 to 1, right, on these objectives. And you can see, you know, you're reducing excretion tremendously. And if you think about how much protein that is, you're talking about 1.5 pounds to 2 pounds of soybean meal every time you make that jump, right, on an equivalent basis. So it's not insignificant. So if you think about what this means, moving most cattle from 0.71 to 1 on a productive N to urinary N basis to a 1-to-1 results in about a 50-gram reduction in nitrogen intake and a proportional reduction in urinary nitrogen. That's about 1.5 pounds of soybean meal equivalent, as I just said. If we go back to the Morris equation, reducing that nitrogen excretion by 50 grams will increase nitrogen retention, or ME, by about 0.73 mcals, and this could be partitioned to milk or milk components. It reduces the environmental impact, reduces the feed cost to improve, hopefully reduces the feed cost, improves income over feed cost, but it also results in an improvement of energetic efficiency, right? So we've integrated the two now. So now I want to change for just a minute. So that's the how do we get the nitrogen under control? We really got to focus on what she's peeing out the back end, all right? Here's where I think we have to learn a little bit. About 10 years ago, over 10 years ago, John Cole published a paper on the upper and lower bounds of genetic capacity for Brown Swiss, Holstein, and Jersey, and you can see the upper bounds for the Holsteins was about 35,000 kilos, or 75, 80,000 pounds of milk, and the lower bounds was about 11,000. And if we look, and this isn't, we've got the Wisconsin cow in Japan that just kicked these two cows in the butt, right, by quite a bit. But, these cows are not high genetic merit cows, made one heck of a lot of milk, right? And now their upper bounds are about 150,000 pounds of milk, and their lower bounds are where we thought they were, just a little bit higher, right? It's whatever they produced. So these are two real outstanding cows. I will argue that these cows are not necessarily unique in our herds, right? If you assume that, based on what John Cole and Chad Deckow put together, the genetic capacity for milk yield is about 75,000. However, I live in Cayuga County, New York, about 18 miles north of Ithaca. I have a lot of cows around me. I can touch about 45,000 cows in 20 minutes, right? There are some high-producing cows in those herds. And these aren't isolated cows. These are cows at peak, right? We'll see cows 186 to 214 at peak and over 44,000 pounds of lactation. And these are in herds that are just regular herds. You drive by and I stop and I look at them and I think, what makes these cows do that? And I think there's a lot of cows and herds that have this capacity. That leads to the question, what do we have to do to get them to turn that on and keep the pedal down, so to speak? All right. Well, just, and I had to do a talk in Europe here sometime in the last 6 months, and they asked me to come talk about the 40,000-pound cow, and they thought it was going to be theoretical. But I brought some of my cows with me, right? There's 4291, third lactation, 51,600, 2,000 pounds of fat, almost 1,700 pounds of protein, 124 pounds of milk a day, 4% fat, 323 on protein. That is a 417-day lactation. I'll give her that. I don't care. I got 30 other cows I could show you from two herds, just in a random selection, right, from Cayuga County. We got really good cows out there, right? And we know how to balance these diets, sort of, right? The point is we got cows that are changing. But I think there's something that we aren't really looking at. So because a lot of these guys, if I talk to the owners of the herds, they'll say, I'm not focused as much on milk volume, Mike. I'm focused more now on milk components, right? And we all know why that's happening. So if I use one of Clay's slides here, and this is Federal Milk Marketing Order 30, and we look at milk fat over 10 years, we see a big change. We see the seasonal effect. But, from 2010 to 2019, and I got to update this, we see, just over 0.2 of a shift, right? This is the effect of genomics. A little bit nutrition. We finally got the unsaturated fatty acids out of the rumen, and that helped, right? And maybe did a little better job on amino acids. And, unlike the federal order that I live in, these guys in 30 are actually doing a better job on protein. If you look at Federal Order 1, boy, we don't see this kind of a opening, this change over time in the protein. So that bothers me that, the upper Midwest is doing better than the Northeast in milk protein, but we all look the same on fat, right? And there's lots of reasons for that we'll get into. Right, so cows are changing. Well, I think this is the thing that really, I spoke at the federal order hearing. I was the token biologist to kind of explain this and why they have to upgrade the equations more often. And they said, how often we're going to have to do this? I said, about every 5 years, right? And anyhow, if we look at this, right, here's the real advent of genomics, right there. took a long time to get to 0. It only took 9 years to go half that distance. And that curve is almost exponential, which means what? These calves, in 1 year, a calf born today and a calf born next year are equivalent to 6 years of selection 20 years ago. They're moving fast, right? Wiggins published a paper on that. What Wiggins didn't account for is he didn't account for all the IVF stuff that's going on that just collapsed the generation interval to virtually nothing, right? So these guys are, it took 56 years to go to 0, took 9 years to go to half that distance, 6 times faster rate of change. When I ask people, is protein moving the same way, everybody shakes their head no. Au contraire. And this is really troubling for me, and it should be for a bunch of nutritionists, because we can move fat pretty easily. Why aren't we moving the protein? That's the problem I'm trying to figure out right now. Why can't we move the protein as easily as we move fat? Right? And I think there's a bunch of reasons for that. Might be a little more complex than I'm expecting, but we'll find out. But the same kind of thing, right? Over 51 years, and hey, we went half the distance, right? Went 42 years to get to 0, 9 years to go almost about, not quite halfway, not quite a 5 times faster rate of change. So these cows are changing. I'm going to argue that their amino acid requirements are higher than we're expecting. I'm going to argue that their fatty acid, I think they have fatty acid requirements given everything that they have to do. We don't fully understand that because we've not thought about fat as an obligate requirement like amino acids. But I think that there are some indications that on an energetic basis, we probably should start thinking that way. The other thing that we need to do, and I'll give you some evidence of this a little bit, and we got more coming. When we look at amino acids and de novo fatty acid synthesis, right, because this is where we're going to make all of our hay on getting more fat in the milk, unless you're going to get it off of some palm and oleic, because this should also have mixed in it. One of the things that we're realizing is lysine increases the enzymes related to de novo fatty acid synthesis, and I won't read all those enzymes, and it upregulates FABP and SREBP1, right? And this is modified with the presence of palm and oleic, right? In other words, there's an interaction between the availability of the amino acids and the availability of certain fatty acids, right? Which means we're integrating that efficiency. Additionally, methionine and leucine increase the expression of SREBP1, which regulate fatty acid synthesis. And we can look at arginine, that also plays a role, right, in all sorts of things. And when we look at fatty acid synthetase, it elongates the fatty acid carbon chain. When we look at the amino acids involved in that, histidine, lysine, serine, and cysteine, and fatty acid synthetase expression is decreased in histidine and lysine deficient liver cells. It's the same pathway, so that would make sense. Alex is going to talk about histidine. This is a good place where we should probably say, hey, we need that for milk fat synthesis. Well, who would think it, right? An expression of it's increased by adding both non-essential and essential amino acids, right? So I think the idea that amino acids are required for things other than milk protein synthesis are really important. We generally don't think about it that way, and I would argue that I can move fat expression in a cow better with amino acids, and I can move amino acids or milk protein faster with certain fatty acids, right? So with our version 7 approach, we tried to integrate, amino acid requirements based on energy to kind of bring them together. Right? This is the only slide I'm going to show. Most of you are somewhat familiar with this, 1.14 grams of methionine per mcal and 3.03 for lysine, 3.03 grams per mcal. So I'm going to show you a couple studies, and I'm going to show you a couple herds. So we did this rumensin study. It's a rumen modifier, had nothing to do with amino acids, 192 cows, 16 cows per pen. Many of you have seen this, but I'm going to reiterate it one more time because it kind of ties together what I was saying. Because when I saw these cows do what they did on milk fat, I had to go back and figure out what allowed them to do that, right? Because what happened, though, is we fed more methionine and lysine in this experiment than we'd ever fed in any other experiment, and that was all based on what we had learned from version 7. Those cows started at about 4.1 and 3.1 on fat and protein. There are the diets. These will be shared with you, or the baselines. You know, cows were about 71 to 72 mCals, so they got about 81 grams of metabolizable methionine and 229 grams of metabolizable lysine, right? For many people, that sounds like a lot, right? And I've had people say, no way in hell, right? It's important, though, that the histidine levels are similar to the methionine, right? And we've learned that if we don't do that, we don't get the same effect. So there is some interaction there. Haven't had time to really chase that down, okay? And if you look at these cows, right, by the time when we put them on study, they were about 120 days in milk. On average, they're about 190 days in milk. You know, they're about 27 kilos of dry matter intake. They're running not quite 40 kilos of milk. Energy-corrected milk's running somewhere between 45 and 47. Now, here's the milk fat, 4.6 to 4.72. Milk true protein, 3.35 up to 3.39, right? What's interesting is that's with rumensin, right? And you guys, almost everybody would say when you add rumensin, milk fat's going to go down, and these guys actually went the other way. Okay, so this was fascinating to a bunch of us, just crazy to some other people because they just couldn't believe Holsteins could make milk fat like that. Neither did I. We all had to learn, right? What was interesting is that the de novos and the mixed fatty acids were greatly increased, and that rumensin actually enhanced that, and that makes sense. If we're getting more propionate out of the diet, then we're going to drive more ATP, more glucose, more insulin, and maybe some more IGF-1, right? So we're all going the right direction on how we're going to make some of those things. And we had plenty of lysine, histidine, and methionine in there to allow that to happen, right? And Barbeno, you know, my joke is Barbeno said that can't be real, those can't be Holsteins. And when I asked him why that is, that's his Holstein data, and there's those cows. Right, and there's the jerseys. He thought these were jerseys. He thought I was kidding him. But no kidding. Back to the nitrogen efficiency, though, if we look at the initial diet to the treatment diet, we increased productive nitrogen, we decreased urinary nitrogen, and we moved the ratio, right, which is in the end. And more importantly, there was about an 8.1% increase in energetic efficiency. Right, so it's not just nitrogen efficiency. We're going the same way on energy. Another study was about rumen-protected methionine, and we looked at lysine. And don't forget about histidine again, 144 cows, replicated pen. We held the lysine constant at 3.2, and histidine was fed at the highest methionine level. Methionine was fed at 0, 1.05, and 1.19 grams of methionine per mCal, 14-day covariate, 85 treatment, 84-day treatment, 75 multipares, and 25 primipares. So in all these studies, we've got a bunch of primipares cows just to fill the pens. So there's our titration on the methionine. Dry matter intake's constant. Milk yield didn't really change. Energy-corrected milk yield, there was a significant difference between the no treatment and the treatment. What's interesting, though, look at the milk true protein, 309, 324, 334. We didn't see the big milk fat response, but we had to use a diet that was already at the herd because we had a new feeder and the manager of the herd didn't want us to throw one more wrench in there. But we still managed to, at the highest level of methionine with the lysine, we still managed to pull up a nice change in fat, right? So again, integrating those things. And then if you look at de novos, Barbeno, one more time, Barbeno calls me and he said, this was the orange treatment. He said, who are those orange cows? I said, why are you asking me that? He said, well, those de novos and those mixed fatty acids, we could make spreadable butter right out of the refrigerator with those cows. You got to go get some milk fat from those cows so I can make butter. I said, you ain't got time for that, and I don't have time to get that much milk just for those cows, so we'll have to save it for another day. But again, these cows really surprised us. Even though we didn't move milk fat quite as much as we wanted to, we did move de novo and mixed significantly, right? And then if we looked at, again, we talked about being 1-to-1, where our lowest treatment was 1 to 2 to 1, and by the time we added all the amino acids in there, we're up to 1.38 to 1. We've never had a group of cows behave that way before. Right? Tremendous nitrogen efficiency if you're thinking about how much you're not putting out in the urine, and given that they're putting more in the milk, right? So from an environmental perspective, this is a great group of cows, right? And this is what we should probably be striving for. You know, urinary nitrogen down to 181, productive N at 250. Boy, those girls are cranking, okay? Real quick, just a couple more slides. Southern PA, I work with a bunch of nutritionists around the East Coast here and there when I have time. Helped a small group down in Lancaster County, said, hey, you know, they said, we got to get some more milk fat out of our cows. I said, I got some treatments, if you can get them to implement them. Milk fat in both herds was about 4.2 and milk protein was about 3.1 before the dietary change. The cows held their milk fat up to 4.64 and 4.76, these are Holsteins, and milk protein up to 3.48 and 3.46, okay? So it's not just the research cows that can do this, we can do this in other herds. One other farm, real quick, this is a herd I work with in northern New York, they're milking almost 4,000 cows. It's a fascinating place. We have been working with the nutritionists in the herd, we've been doing this over 2.5 years. In fits and starts, right, because some things don't always work right in a herd that size. They finally got their own grain handling system, put in a bunch of bins, roller, roaster. So we got the amino acids right, we got the fatty acids right, we got the histidine, methionine, lysine up there where we thought it should be, and the cows moved up to about 4.4 on fat, right? And these are cows that are averaging about 94 to 95 pounds of milk, right? So this is a really good herd. And we moved the protein up, right, to about 3.2, 3.3. And then they went and got some Plenish beans. And this was interesting. And they said, we're going to layer the Plenish beans on top of this. What do you think? I said, well, we're going to learn something. And what happened was, the first thing that happened is they moved from about 4.4 up to about 4.7 fat. And about 2 weeks later, or 3 weeks later, and this is always interesting, in the protein always lags the fat. The fat comes first in all of our experience, and then the protein creeps up. And so all of a sudden, we're up at almost 4.8 fat, and 3.4, almost 3.4, almost 3.5 true protein. These are on Holsteins. Okay? So the amino acids, the Plenish beans, change up the fatty acid profile. What's more, this is back to my point about the cows are changing. Those are genomic Holsteins, 2-year-olds, making about 85 pounds of milk. What do you think of that? That's intimidating, right? You can't make legal cheddar with that milk. I spoke to the New York State cheddar producers or cheese producers about a month ago. They're scared because all this fat's coming their way. We can't make enough protein. So they're going to have to skim the milk to make cheddar cheese because it's a legal definition. There's too much fat, right? And they're like, you got to get the protein up. Well, I'm trying to figure it out. You know, the genetics are there, guys. How are we going to get it? But these guys are close. But even at that level, they have to be at 3.6 to 3.7 protein to make legal cheddar out of that milk without skimming the fat. Right, so we've got a bit of a problem here with our cheese producers, okay? Anyhow, so there's the steps to optimize nitrogen efficiency. You got to determine what's first limiting, you know, and then evaluate rumen imbalance and urinary excretion. If it's high, then work to reduce the soluble protein. You know, within the CNCPS, we look at ammonia balance somewhere between 120 and 140. And we'd like to get the urinary nitrogen less than 180, but you got it work. It takes work. If MP is in excess, you got to decrease that in increments. You know, then you just once you get all that done, now you can focus on amino acids. And I gave you guys those idea where to be on that. It's important. NDF digestibility is your best friend in all of this. The other thing we've learned is don't overfeed fat. We'll find that as we pull the fat back a little bit, we get the cow to make more de novos. If we push more fat, the cows make less de novos. Adam is here somewhere. He showed that very clearly. There he is. He showed that very clearly last year in a study. So yeah, go ask him.